Oh. Oh yeah. All right, so we are smack dab in the middle of fractions, which is everybody's favorite. People's favorite are either fractions or word problems. So the very first stuff we did was just to lay out what fractions could represent, different ways to represent fractions, why reducing them kind of makes physical sense. Yes? You guys all with me? Everybody? I think there's a couple of things I needed to finish up at the end of section 6.2. Can somebody, oh shit. Let's see. Oh, that would help. Can somebody remind me in 2 words or less, what it is about adding fractions or subtracting fractions? What has to be true? And what is it built on? Why can't I just add certain fractions? Yes. And what idea does that relate to, this general algebraic idea? You said denominators. Yeah. What about? Like terms. Oh, good. So, like terms is a general algebraic idea. I can add x and x, but I cannot add x and y. Right? So, I have no idea if you guys really included on this. I don't think we teach it that way enough. When you're teaching very, very young people, you start off with the physical properties, and you start off with the manipulators we work with. And you can add 2 triangles together, that makes sense. But you can't add a trapezoid and a triangle, right? So that is a very physical representation of like terms, but we don't say the words like terms because they don't know that yet. But when you get older students who are still having some trouble with fractions, if you just said, like terms, I can't add x and y, but I can add y and y, that's fine. So like, that's why this problem is so damn easy. You can do it, Jeff. 4 sevenths plus 2 sevenths. Wow, that is strong. Okay. That was bright. Right? 4 sevenths plus 2 sevenths is 6 sevenths. The same way that 4x plus 2x is 6x. It's exactly the same idea. 4 somethings plus 2 somethings is 6 somethings. So things get weird when the bottoms aren't the same, right? You will have students that do this. So I have made a mistake there. Yes? Please don't take this to your McGee and say, listen, look what Jeff wrote down. You need some help. I don't know if he's off his meds. What mistake did I make, of course? Yeah, one thing I did was I added the denominator. So like in number 1, if you get a student who does this, the very first thing you show them is like, well, what if they did this? And you're like, well, you didn't make it 14 on the bottom. Why would you suddenly make a new rule, right? You're trying to establish that math processes don't care what they're operating on. Does that make any sense? Like, in number 1, have we established that you do not add the denominators? That is what number 1 says. And on number 2, they added the denominators. And you're like, wait a minute. You have a rule you show you understand, and then you didn't apply it correctly, right? On another level, it's why were they able to do number 1? Because they're like terms. I got 4 somethings plus 2 somethings is 6 somethings. I got 3 somethings plus 1 something else. I can't put those together. All right. And I've seen students in my classes here at Grossmont make the number 2 mistake. Yes? Okay. So just to make this really clear for everyone. No. Okay. So of course, what do we do then? How do I make this work? What do I do? Yes? What's the first you need? He needs a 3. He needs a 5. And in this case, it's really, let me rewrite this and let me make a couple points. You guys remember that phrase I used before, relatively prime? You guys remember that phrase? Okay. You're all like, I barely remember you. More. 5 and 3, you agree they're relatively prime. That phrase does not require either number to be prime. 8 and 15 are relatively prime. Why? Why are 8 and 15 relatively prime? What did that phrase mean? Are you guys doing okay? It's been a while. Did you guys have an okay weekend? Did the weekend go okay? I'm really sorry. Some of you guys are looking away from your minds. If you had a bad weekend, sorry. If I could do something, I would. So, relatively prime. Why are 8 and 15? Why are they relatively prime? Is either one prime? Eight and 15. Is either one of those prime? No, but I am saying, because I'm insane, that they are relatively prime. Why? Why are they relatively prime? Relative to each other. What's prime mean? I'm sorry. What's prime mean? Only divisible by itself in 1. Relatively prime carries that idea to how you compare two numbers. What's the biggest number that goes into both 8 and 15? What do they share? They only share 1. 1 is the only number that goes into both, right? You see how it's related to the idea of a single number being prime. Relatively prime, you have two things you're comparing. Related to each other. How are they related to each other? These guys have nothing in relation to 1, so they're relatively prime. Maybe. Are 8 and 14 relatively prime? Are 8 and 14 relatively prime? No. Why? They both have a factor of 2. Okay. You guys would. So this idea of relative prime has come up earlier this semester. It's a very important idea. You all agree with me that 5 and 3 are relatively prime? They're freaking prime. So does it make sense that two numbers that are each prime will be relatively prime? They can't have anything in common because they're already prime. They barely have anything in common with themselves. Okay, this class sometimes borders on the psychology of numbers. When they're relatively prime, they're each missing each other. The LCD will be the multiplication of the two bottoms. The first dude needs a 3, the second dude needs a 5, so they'll both end up with 15 on the bottom. Do you guys see that? Okay. So like he did up here, he needs a 3, he needs a 5. 9/15 plus 5/15 is 14. 15ths. Okay. So just to kind of extend this idea, if I had, what you got, Jeff? 7/8 plus 1/15, based on what we just said a minute ago, what would the LCD be? Are 8 and 15 relatively prime? Are 8 and 15 relatively prime? Yes. I need you to get this idea. This is a cool idea. You should have been taught when you first learned fractions, and if you weren't, I'm sorry. 8 and 15 are relatively prime. The LCD is going to be 8 times 15. when the two bottoms are relatively prime, they are missing each other. That's cool to know. LCD is easy as shit. If the bottoms are relatively prime, you just multiply them together, you get the LCD. 8 times 15 is the LCD. What's 8 times 15?
124 or 120.
Okay, so yeah, it would be 4 times 30. You could do a compensation thing, but yeah, 120. So this will be, this guy needs 15, this guy needs 8. So the bottom is going to be 120. What's 7 times 15? 105. 1 times 8. I get 113 out of 120. I believe that's prime. I mean, not prime, irreducible. Okay, how we doing? How we doing? Have you guys ever noticed this about fractions? Alright. We're going to talk about so many ideas in here that give you a more complete picture of what you're going to be teaching. You're not going to tell your students every damn thing I tell you. You're going to be ready if students have interesting questions. You never... Now listen, the best thing a teacher could say, and I've said it several times, is somebody asks me something kind of on the edges of what I've been talking about, I'm like, I don't even know, I'm going to look that up because it's school, right? So feel free to go, you know what, I'm not really sure. I'll look that up and tell you tomorrow. But you also want to have enough, if somebody asks a question like, oh yeah, that's actually this, I wasn't going to really talk about that, but that's this and this, you know. Yes?
This is my 2.
This is 6'2". I'm kind of reviewing what we've gone over. So it could be 6'1", 6'2", I can't remember. I just know stuff, I don't know where it is in the book. How we doing so far? Because listen, I understand a lot of us have issues with fractions. And if you think about it, it could be holdovers from when you were little. And I was talking to somebody earlier today about when you get a student's work and the answer is wrong, one of the things, if you come away from this class with anything, it's even if the answer is wrong, try to see if any of the logic was right. Make sure you include that in any discussion or anything you have with the student about the problem, right? Because the student can have a very creative way to try something, and they tried something and they forgot a number and it didn't work. But if you don't even take the time to go, oh yeah, dude, the way you thought about this would have worked. You just left the 1 out over here and it would have worked. That's really, if you never do that for them, they're going to give up on that idea. They're going to feel like, I thought I knew what was going on, I don't. And then they shut down. Okay, maybe. Not to put a lot of pressure on you, but there will be a lot of pressure on you. That's one thing I don't envy about you, is you're exposing students to new ideas, and it's on you to give them a good foundation. Okay, that's that. So, if I have two denominators that are not relatively prime, what you got, Jeff? I don't know, dude. Here we go, perfect. So LCD is related to LCM. So I want to remind you a really nifty procedure we learned when we were doing GCF, LCM. Can you guys tell me what the GCF is of 12 and 8? What's the GCF of 12 and 8? Good, 4 goes into both. It's the biggest number that goes into both. And what's 12 times 8?
96.
Yes. So there's a rule we actually talked about back when we talked about LCM and LCF, GCF and LCM. If you take the product divided by the GCF, 96 divided by 4. What's 100 divided by 4? 25. So what's 96 divided by 4? 1 less 4, 24. That's the LCD. Yes? Why does that make sense? Why is 12 times 8 not the LCD? Because 12 and 8 are not relatively prime. So 12 has a 4 in it. 8 has a 4 in it. Stay with me now, come on. I know. Math is boring and shit. 12 has a 4 in it, 8 has a 4 in it. If I multiply them together, don't I get an extra 4? I don't know if you guys are with me. 12 already gives a 4. If I multiply 12 by 8, I'm going to get another 4 that I already have. That's why this makes sense. If I divide by the number they both have, I don't count it more than I should. That's why if they're relatively prime, what's the GCF? Frickin' 1. That's why their product is the LCD. Okay. Now, 12 and 8 you really shouldn't have done. I had to do all this problem, but I wanted to show you a smaller example of how this works. And then you give this guy a 2 to make him 24, 3 to make him 24, 14 plus 15 over 24 is 29 over 24, and then you can make it mixed number, whatever the hell you want to. Okay. I like it. Yes?
I'm sorry, could you explain number 5 again, please?
Oh, okay, sorry. Yeah, it's not really helpful when your math teacher makes Roman numerals as how he's counting things are. You mean down here?
Yes.
Okay, so LCD is the smallest number that both can multiply up to be. They already both have a 4. So is 12 missing all of 8? No, because they already both have a 4. This makes sense what I'm saying. So this is just getting deeper into the idea of LCD. I'm trying to build them both up to be the same number. They already share something. So if I multiply them together, I've got 2 4s in there when I didn't need both. And that's why dividing the 4 out makes sense. Now the numbers are small, so you could have done the set method where you build up multiples of each. You could have done all these different things, but just to show you the general idea. This works always. And then just to remind you, this is not even my favorite way to do fractions. And I know the only humans on earth that have a favorite way to do fractions are math teachers. I understand that, but here's my favorite way to do fractions, in case you're curious. So if I have to do 11/15 minus, what you got, Jeff? Let's do 7/40. Yeah, look at that gross stuff. I like it. So I kind of mix a few things together, and I'm pretty sure I've shown you this already. So we understand the basic idea is I cannot do the subtraction because they're not like terms. They are numbers, so I can do more with numbers than variables. So if it was x minus y, I'm done. But it's number minus number, maybe I could do something. So I'm trying to make the bottoms the same. Can anyone see the GCF of 15 and 40? 5. 5 times what is 15? And then 5 times what is 40? This is a more in-your-face application of the thing I just did. And I think it's an easier to get a hold of application. They already both have a 5. But what is the first dude missing the second dude has? No, the first dude, what's he missing? What's the first guy missing on the bottom that the second guy has? 8. You guys see that? If you identify what they already have, then you can see what they're missing compared to each other. So do you guys see that? If you're going to GCF, break it down. The other piece is going to be what each one is missing. Yes? So the first dude, if I give him an 8, and if I give the second dude, what? What's he missing now? 3. Then both bottoms are freaking 5 times 8 times 3. Yes? That is to me, when the bottoms get worse, and you're like, I don't want to write multiples of this shit. Then you do this. You're kind of building them up based on what they already had in common. Maybe. Now, obviously, this is not what you do with really tiny people who are just learning fractions. But for you, you need to have a more complete understanding of like the eventual best way to do a problem and what it's built on, and then you end up buying into GCF LCM more. Because those ideas become really important. Yes? Maybe? Okay. So then this is, what does the bottom become? What's 5 times 8 times 3? 120. I don't know, that seems to be a favorite number of mine today. Let's see. And what's 88 minus 21? 67. Do you guys think I could reduce that? 67 is not even. 6 plus 7 is 13, which is not a multiple of 9 or 3 or anything. I mean, it doesn't look like 67 has many factors in the first place. I don't think it's about like this. Good. Maybe. Be real careful. Obviously, in a quiz or something, if you can reduce the answer and you don't, you're going to lose points. Because that's a part of the problem. Yes? Okay. Okay. What was the last thing? Oh, yeah. Can you guys remind me what compatible numbers meant? This is still 6-2. This is the last thing we haven't talked about in 6-2. You guys remember compatible numbers? Yeah, they're numbers that can hang out. You know.
Like 8 and 3 and
There's a not some time. It was 8 and 3.
Oh,
8 2.
8 and 2, that's what I meant.
Or-
8 and 3.
I always mix up 2 and 3.
Yeah, I was like 3.
I always mix up 2 and 3.
I did 10.
1, 3, 2, 4. Okay. I'm with you. Okay. Right? Those compatible numbers. 18 and 12. 52 and 48. Right? Things that come together make a nice whole number. Yes. So can you see that with fractions? Can somebody tell me compatible number with 4 sevenths? 4 sevenths.
3 7s.
Why 3 sevenths? Because it makes a whole 1, yes? So if I had 4 7s plus 3 8s plus 3 7s, what would I do? Be very specific. Well, Jeff, what I would do. Don't just tell me you put 4 7 3 7 together. No. So what rules would you use? What are the numbers that you want to put together because they're compatible? The ones we just talked about, right? You guys with me? So what rules do you have to use to get them together? Good. And what do you call that when you move parentheses? Associative, kick ass. Parentheses, they're asses. So when they move around, they're associative. Whatever's going to stick in your head. Yes? But you don't want to use that first, because then you would just move it to be 4 7s plus 3 8s, and that sucks. What do you want to use first? The other one. Commutative. Yes. Yes. Don't put people into communes. It's commutative. So I would use commutative, which would be look like this. They playing pool upstairs? And then I would use associative, which would look like, good Lord, Jeff. So I have to move those around. So then when I move the parentheses, I've got the 2 I want trapped. And like you guys said, what's 4 7s plus 3 7s? 1. Plus 3 8s? Done! Kick ass. So if anything's going to be good about fractions, it's finding 2 fractions that go together and make a nice whole number. Shit, yeah. So there's compatible fractions, compatible numbers, extended fractions. Kick ass. So all the mental math stuff we've done before. What's about compensation? Do you want to do that next? I can do that next. Why not? Geez, today's a really good writing day for me. So what about compensation? What about compensation? what about, let's see, how does the idea of compensation help me out here? Compensation. Compensation is sort of using the idea of compatible numbers, but it gets what it needs from another number. Right? Remember, compensation was when you get paid by somebody, so one number is the guy paying and the other number is the guy getting, yes? So what does 5 and 9/11 need to get up to 6? You guys agree it's less than 6, obviously. Yeah, it needs 2 11s. Or like Grace said, 2. Yeah. Where can you steal those 2 11s from? You can't just give it to them out of nowhere. Well, the only other guy in the whole thing, right? So I can write this as 5 and 9/11 plus 2 11s plus 2 and 2 11s. Yeah, so I steal 2 11s from him, give it to this guy, 6. And then what do I get at the end? What's 6 plus 2 and 2 11s? What's 6 plus 2 and 2 11s? 8 and 2 11s, yes? Okay, maybe. It's exactly the same idea as compensation that we've done in the past. The exact same idea, just with fractions. And fractions makes everything better. It's looking for raised eyebrows. Bless you. Does anyone remember another mental strategy we used? What's the word? Distribution. Do I need to go over that? Let me think.
You did a little last week, I think, or yeah.
Yeah, I can't remember. I think I already did an example of that,
We
but
did like borrowing.
borrowing, which everybody really enjoyed. Well, distribution would be, we haven't really gotten to multiplication yet. That's the problem. That's what my hang up is. I'm like, there's some reason I can't do that yet. Wait, we haven't talked about multiplication yet, officially. But here's one. What about equal additions? Stay with me now. Equal additions. Who remembers what the hell that had to do with? Yes?
Adding the same number to both sides to get,
Both sides. When you say both sides, what do you mean? Both parts of a what kind of problem?
addition?
No.
Multiplication.
No. I know, the word additions makes it sound like it must be talking about addition, but this is when I had to do something like, you can do it, John. So a problem we would have seen in the past would have been something like 42 minus 19. But if I add 3 to both, their distance stays the same, so the answer to the subtraction problem stays the same, right? Do you guys remember that? That's equal additions. Raise both parts of a subtraction problem the same amount, or lower, because subtraction is all about the distance. And what if I do anything that makes the distance stay the same, the answer is the same, so I am allowed to do it. Kick ass. So of course the same thing happens with fractions. Same thing happens with fractions. So what if I have, here we go. That's kind of the worst kind of fraction problem to see, because you're subtracting something that's overloaded in the fraction part. The first guy didn't even have a fraction, so it's like, what do I have to add to 7 4/9 to make it become 8? What does 4/9 need to make it become 1? 5 9, yes. Grace is telling me to steal first. Look. So if I add 5 9 to both, the distance between them will stay the same. So this becomes 60 and 5 9 minus 8. And what's that? If you do it, what's 60 minus 8? 52, and you got 5/9 that it didn't touch, yes? Is that cool? You can see that? 60 and change minus 8 is 52 and change, right? So I kind of effectively what I did was I shifted the fractional part to the first dude, and that's where I want it to be. Because then it's just left over at the end. You see that? I know you can make mixed numbers and bullshit, but it's kind of good to realize that all those mental strategies we had before still works. It's a lot easier to do this in my head than it is to make a mixed numbers, keep track of everything. Yeah, I wanted to do, let's see. Here, I want to try some, let me see. Let's try this. I like this. What if I had 5 2/5 minus 3 4/5? I think that's the problem from last time. Do you see how now if I look at it through the lens of equal additions? I'm going to show you something really weird with this problem. But we're going to first do it a less weird way. So what do I look at to consider equal additions? Which part of this do I wish was different? Besides the whole thing that existed. Which part of this, which of the two pieces do I wish was a whole number, for example? Yes?
Oh, I was gonna say either one of the numerators.
Say again?
Either one of the numerators.
Oh, I see. Not which part do I want to make a different number, but which part do I wish I could change legally? Like, how do I say this? So I want the second piece to be a whole number, yes? Because it's easier to subtract a whole number than it is to subtract a mixed number. You guys with me? That was the whole purpose of why we did what we did in part A. So to do what we did in part A, what do I add to both? Grace has got it locked in. 1/5. So if I add 1/5 to both, what's 1/5 plus 3 4/5? 4. And then what's 5 3/5 minus 4?
1.
Done, yes. What's 53 minus 40? Oh, that guy found through. What's 53 minus 40? 13. Did you give a shit about the 3 or did it just get written in the answer? Just got written in the answer because there's a 0 there. So if I make the second dude not have a fraction, this guy's not going to change. That's why I only care about the whole number parts, right? It's whole number and 3/5. Because he's not going to change. Okay, maybe. Now, let me show you the really weird, trippy way. Do not show this to little people. It's illegal in most states, except Missouri for some reason. No, I'm trying. I'm going to do, only a math person would do this. You ready? What's 5 minus 3? That's insane. What's 2 minus 4? No, 2 minus 4 is what? Now, what's 2 minus 2/5? 1 and, you can do it. 2 minus 2/5 is 1 and 3/5, which is the answer, correct? That's more of a mathematical side note. Do you guys see that? But I just can't help but show you. Do you understand why you shouldn't show a little person this? Because then they'll start doing all kinds of weird places. So if you didn't like what I just did at all, you never have to do it. It's just me showing you something kind of nifty. Okay. Made it? Screw you, Jeff. Fractions suck already. What are you doing? Okay. I think. Oh yeah, that's right. One last thing in 6.2, estimation. Are you guys placing bets on what I'm going to do next? So estimation. If I wanted to estimate 7 and 5/17 plus 4 and 3/11. First off, if you see this kind of problem, you're like, please, dear God, tell me you want to estimate this. Because do you want to make LCD and all kinds of stuff? Do you want to make up mixed numbers? No, I don't want to either. So what is the most basic way we have to estimate? Think back. When I said to estimate something, making, okay, rounded. But if I put that together with another idea of like high and low, right? So if you round both of these down to a whole number, what do they become? Round them down. Round them down, what do they become? To a whole number. 7 plus 4. And you get? That's crazy. Now round them up to the next whole number. Now that's where the book would end. And it would say, okay, that's my range estimate. Of course, we talk about the fact, what would we do? Because we're not crazy. What would we do with 11 and 13? Average them. So our estimate would be 12. Okay, because that just makes sense. If I know the low and the high, I'm going to average them and get like 12 in the middle. So that's my average. That's my estimate. You guys understand? So it's the same idea as range estimate with whole numbers. It's exactly the same idea. You round it to the next integer down, you round it to the next integer up. There's your high, your low, and your high. Okay.
Hey, where'd you get the 12 from?
This is a low estimate, this is a high estimate, so if I average them,
Oh, okay.
I get a decent, just straight up estimate.
Oh,
Yeah.
okay, gotcha.
Okay. Yes?
Weird thing, but I've noticed that you always have to round down above the round up.
Yeah, for me, it's always low to high.
Okay.
I like to see it as low to high. Yeah.
So it's not like something you have to do, it's just.
No.
Okay.
It's like somebody saying, yeah, your kid could be anywhere from 13 to 7. You know, like, ooh, what? 7 to 13, right? No? Or is that, am I the only one that would be bothered with that? Well, if you join us here, you can make anywhere from $80,000 to $20,000 a year. Whoa. So yeah, we normally do low to high. Okay. So let's do this. Let me shut up for a little bit. Everybody can, under your breath, say thank God. We're going to watch some little people work with some of this stuff. I don't think I've shown you them working with any fractions yet. Correct me if I'm wrong. If I show you one you've seen before, let me know. I'm hoping to finish 6-3. We'll see if that happens. Oh yeah, we haven't really talked about next quiz, because I think the last test went up through 5-1. Is that my memory working right? Thank you. Okay. So we should have a quiz on like 5-2 and 6-1. So if we, okay, do you want a little democracy for a moment, just to see how it feels? Do you want to quiz this Thursday, or do you want to quiz next Tuesday? No, that's later. We have a silly holiday on Tuesday. You guys know that? No. November 11th, I think. So for some reason, Veterans Day, they decided we're going to be in class on Monday. You have Monday classes, and then Tuesday's a holiday. So like, no consecutive days off for you. Too bad. Whatever. I almost know the answer is going to be a week from today. Is this true? Okay. So let's make it official. We're going to have a quiz on 5-2 and 6-1. If I make it next Tuesday, I'm going to throw 6-2 on there also, because we finished 6-2 today. So next Tuesday, we'll have a quiz. Yeah, next Tuesday. Quiz 5-2, 6-1, 6-2. Is that understood?
So you said the 11th, right?
Yeah, I think the 11th, is that a Tuesday?
Yeah.
Yeah.
It's like 3 weeks from 2 weeks from now.
Okay. I know, it's weird. It's almost freaking November, it's almost freaking December, it's almost freaking 2026. What the shit?
Do we take Veterans Day off or?
That, I think,
That's
is,
the 11th.
that's Veterans Day,
Yeah.
that's the holiday, yeah.
On the 11th.
So we have Monday classes, and then we have Tuesday holiday, and then we have Wednesday classes, yeah.
Wait, you mean? So then are we
taking it the 4th?
Do it again.
It's the 4th in the middle.
It's the 4th. Because Veterans Day is on the 11th.
That's what I'm saying. So
Oh.
I couldn't remember when I'm sorry, I said that. I couldn't remember if it was sooner or later. It is later, so next Tuesday's fine. So we're taking it next Tuesday, which is the 4th, because the following Tuesday is the holiday. It was a neat trip we just went on. I think our next test is officially set for the 13th. Somebody just asked. Okay. Love you guys. Alright. Everybody prepare. I'm going to turn the lights back on. Everybody ready? I'm going to bring them up slowly if I can. Let's see. Yes. Oh shit, too many came on. Need this stupid one go away. Nobody likes you. Alright guys, let's see. So can somebody remind me what multiplication is fundamentally? Yes. So can somebody tell me what 4 times 2 is using what you just told me? Oh shit. How many groups of what adding? 4 groups of 2. Kick ass. So it'll be 2 plus 2 plus 2 plus 2. Stay with me. So I start with nothing. Yes? This is blank. And then I put down 4 2s. Stay with me. So then what's 4 times 1/5? And of course this comes out to be 8. It's crazy. How would I do 4 times 1/5? What happened? How would I represent it the same way? Yes, 1/5 plus 1/5. That's crazy? I like it. Which actually makes the word we use for the symbol for multiplication make more sense, because you just said we write 1/5 4 times. 4 times 1/5. Okay, now, things get really, really physically trippy when we start doing stuff like 1/2 times 6, because what would that technically mean? How many 6s do I want to write down? Half. So if I change to a, watch this. So if I do 2 times 6 and I use a set model, do you all agree? I start blank. What is happening? You guys are. It's like both corners of the room. It's weird. Okay. About what? Okay. So 2 times 6. I start blank, yes? And what am I gonna put down? How many whats? Groups of what? How many groups of what? 2 groups of 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and that's why the answer is 12. It's great. That kind of helps us figure out what to do here. How many groups of 6 do I want to put down? Half of a group of 6. So if a whole group of 6 is 1, 2, 3, 4, 5, 6, I want to put down half of the group of 6. So, fractions, and it's going to get trippier, of course. This still, you can see the physical sense that it makes, yes? But fractions start to kind of lose obvious physical sense. You can still make physical sense out of them, is what I'm going to try to do. What about this? Doing what we just did. Can you guys do this purely visually? 1.5 times 6. Don't say anything. Try to do what we just did. 1.5 times 6. Don't say anything. Try to do it with a set model.
Draw it out.
Yes.
Okay.
Or you know, I don't know. I'm not gonna walk around with paper. So to a blank area, what are you gonna put down here?
A circle.
A circle.
And
Uh-huh. Okay, 6 little dots. What does that represent so far?
the
1.
And then do you do that again? 6 little dots.
Huh?
And
But I'm gonna throw these out. So then I get 9, yes. And of course that's 1.5 times 6 is, right? Okay. Now, that's a very simple little visual example, but of course we all know by now the power of the visual for little people. You could even do this with, physical collections of blocks, right? You might not realize how much you could do with whole blocks instead of those fraction manipulatives. You could still represent fractional operations, but with like whole blocks. 1.5 times 6, one group of 6. Half of a group of 6, you can see the answer is 9. Yay! Now, eventually, you're going to have to go over that because the answer is going to be some kind of fraction, yes?
Would it be safe to say like, you could just like, in this case, with 1/2 times 6, you just do it 6 times the numerator, and then you just simplify the mixed.
But see, that's an algorithm. That's the, and this is what, again, we're going to continue to butt our heads up against the problem parents have, for example. But not even just the problems anybody has. We're like, why don't you just do it the way you do it, dude? What the shit? But we have to always remind ourselves, little people, physical reality, they can hold it, it makes sense. Can I take the physical reality and show them how this works in it? Then they start to accept that this makes sense. And then I can start to develop, we could do stuff like 1 times 6 plus 1/2 times 6, which is basically what we just did visually, yes? Or change into an improper fraction, and all this kind of stuff, yeah. Where am I? There I am. So what about this? What about 1/3 times 5? Now, real quick, we know the answer is 5/3, but that doesn't help a kid understand what 5/3 is. It doesn't help them see why it is that. They don't know multiply across yet. They don't know any of that shit. It's just 2 numbers. We've introduced to them what fractions are. They're numbers. They represent certain things. And now we're going to multiply 2 numbers together, right? We're trying to get them to a point where they'll understand if I put a 1 under the 5, I can just multiply across, right? And that's what parents are like, why don't you just show my kid to just multiply across and weird. I have no idea if you're going to get that, but you might. So 5 sucks because 3 doesn't go into 5. But here's another way. So if we bring in our measurement model and we write up here 1. Why did you draw that first, Jeff? 2, 3, 4. Okay, this will work. That's 5. That's fine. I don't know what he's doing. He's just sitting there. Now, where do you think I can go from here to represent 1/3 times 5? And the answer is kind of neat. Do you see how I literally want to go 1/3 of the way to 5? That's what that really means, right? 2 times 5 would be twice the way to 5, which would be 10 total, yes? 1/3 literally means 1/3 of the distance to 5. So I want to break the distance between 0 and 5 up into 3 parts, yes? Well, if I break, now watch this. If I just break everything into 3 parts, pretend like everything's equally scaled. How many total parts did we just make? Every part I have up there, up to 5, I broke into 3 parts. So how many total steps of a third are there? 15. So now if I want to kind of break this up into 3 steps, it becomes 15 divided by 3. I don't know if you guys are with me. How many total steps? 15 of these steps, yes? And I want to break it up into 3 parts, yes? So then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I want one of them. So the answer would be 1, 2, 3, 4, 5. 5/3, or 1 and 1, 2. 1 and 2/3. Okay, maybe let me stop. Let me stop. Another way to do, a slightly different way to do the exact same thing I just did. If I have 5 objects, and I break each of them down into thirds, and I take 1/3 of each piece. 1/3 of 5 pieces. What have I just shaded in? How many thirds have I shaded in? 5, so it's 5/3. Okay. Now again, on one level, if a parent or somebody saw you have this exercise with your students, they would say, "What the shit's wrong with you? 1/3 times 5 is 5/3. Of course, 1 times 5 is 5. What are you doing?" We haven't gotten there yet. This is purely physical at the moment, right? Maybe you guys are with me. Okay. Let's get to something. Let me see if you guys agree with me. Here, let's try one more of these out. Yeah, let's get a little worse. You ready? 1/3 times 1/2. Oh shit. So how do I represent 1/2? I just plop. There's 1/2. Yes. And I want 1/3 of 1/2. Which really just means cut this into 3 parts, right? Now, if I keep going, if I do this all the way down, how many parts have I cut this 1 into? How many parts have I cut this whole thing up into? 6. So this is literally 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, red fish, blue fish. Okay. So if I just look at this piece, and I go 1/3 of the way towards 1/2. You guys with me? What do I have? Of course, if I go 1/3 of the way to 1/2, there. And the answer is 1/6. And we know that's the answer. Of course we do. And that's when the parents are like, "What does 1 is 1, 3 times 2 is 6 with it?" Well, okay, that's great. That's fantastic. Do you even know the physical interpretation of what you're talking about? So yeah, that's why we start with the physical, because that's what they're grounded in. Anyone else think that's like slightly, you know, somebody's gonna be like, "Of course I do. Remember I said that." Give me points up. That to me is kind of neat. You get the answer out very physically. Okay. Let's get something that you might like better. I don't even know how you feel about this, but I always feel like people don't necessarily enjoy this. This gets a little trippy when I make worse fractions, of course, so we don't keep doing this forever. Something that's slightly better. If I want to look at the same problem, how can you make 1/2? I just take that block, you're not going to believe it. Take that block and do what? Cut it in 2 parts, yeah. And then I just shade one of them. Is everybody with me? So everybody do that with me, right? That's the easiest way to make a half. And then this literally says, take 1/3 of that 1/2, right? So this is kind of a beautiful visual. So going the other way, how do I represent 1/3? Ignore what I've drawn so far. I've got a block. How do I represent 1/3? I cut it into 3 parts, and I shade one of them. How many parts did I shade twice? Out of how many total parts? So the answer is 1/6. So this is 1/2, this block, this column, and if I take 1/3 of that, what I actually get is 1/6. That's fantastically physical, visual. Yes? That's neat. And yes, we all know 1 times 1 is 1, 3 times 2 is 6, and that's quick. But it's not built from the physical, which is where they live. Which is where we live. So, if you forgot you could do this, it's just neat to reconnect. Hey, there's a physical interpretation to this shit. Okay. Maybe. So the answer is 1/6. So you can do that with worse and worse fractions, but again, once they get really bad, I don't want to do this. I don't want to do 11/48. No, Jeff. I'm not going to draw 47 lines for you. Screw that shit. So if I give you this kind of problem, I'm not going to go crazy. You establish an idea, you make a pattern, and then you make a better way to do problems. So when the problems get worse, you don't have to do a billion freaking cuts. Blah, blah, blah. Let me see. Can you guys do the same thing I just did, but with that problem? Can you guys try to represent that problem? Pay very strict attention to where I put 1/2. Yes? So you should probably put 4/5 in the same place. Are there some, like, do you guys know there's like some sicknesses happening? Or anybody's friend sick or something? Because I know there's one student that I know is sick for sure. I don't know if other people you're sick. Alright.
Yeah, that's evening.
I don't mean just like generally sick. I mean currently sick. Okay. That's the great thing about teachers. You get to have your students share with you everything that they have going wrong with them. All the germs they're going to share it with you is going to be great. So up and down, how many cuts do I want to make? What do I want this one to be? I want this one to be 4/5, so I want this one to have 1, 2, 3, 4, yes? And then this way, so then 4/5. 1, 2, 3, 4/5, yes? Okay. And then this way I want 2/3. So then I kind of ignore what's here and I go, okay, let me cut this into 3 parts, so I can make 2 cuts. And I want 2 of those. 2/3, yes? So how many did I double shape? How many did I double shape? 1, 2, 3, 4, 5, 6, 7, 8. And of course, how many total brownies are there? How many? I was trying to do 3. 15, yes, if you count. So, do you understand? A student does not need to know how to actually algorithmically, how to actually computationally do that problem. This is purely visual. But it leads to, well, 2 times 4 is frickin' 8, 3 times 5 is frickin' 15. There's a beautiful shortcut, kids. Maybe, Jeff. In fact, right here, I know that I'm going to have 15 pieces. Cutting 3, cutting 5, I'm going to end up with 15 pieces. So it makes sense that the bottom is 3 times 5. And then I ended up with 8 shaded because I shaded 4 this way, and 2 this way, and that's 2 times 4. So then you can start to talk about multiplying across once you've done several of these physical demonstrations. Then students buy into it more. I can see 8 brownies out of 15. I can see them. If you just show me 2 times 4 is 8, I don't have any grounding. I don't have any connection to it. Why would I buy what you know? All right, teacher, you said it's the way it is, so I'll do it. But no, I can see the damn thing. Okay, so let's make things even weirder. Here we go. What about if I'm trying to multiply mixed numbers? There's so many misunderstandings. Can somebody remind me what the operation is between like 1 and 1/4? What's the operation? Oh, not how do you convert it to improper. What is the literal operation between the 1 and the 1/4? What are they doing to each other? It can't be times, because what's 1 times 1/4? What's 1 times 1/4? 1/4, and is 1/4 the same as 1 and 1/4? So it can't be times. When I say and, what is that hiding? Remember, this is one of the worst decisions in the history of math. You guys don't remember? That's what I said last time. This is 1 plus 1/4, yes? That's what that means. Do you guys see that? Do you guys remember that, I should say? How can you see it? Because you can't see it because of our decision to hide it. Do you see how that's going to become really tricky for your students? Okay. Maybe. So if I wanted to do this non-visually, without going to improper fractions, I would actually have to FOIL. Do you guys see that? Right, so let's not do that. So if I want to do this visually, I can borrow something we did back with base 10 pieces. Believe it or not. I have 1 and 1/4 and 1 and 2/5. Let me write this. 1 and 1/4, 1 and 2/5. You guys with me? I don't know if you remember this when we multiplied based on we would line things up this way, line things up that way, and then we made areas in the middle. So 1 times 1 makes a flat like this, yes? Wow. 1/4 times 1 makes a 1/5 times 1. 1/5 times 1. 1/5 times 1/4 makes something this big, this big. How big is each one of those though? 1/4 times 1/5. 1/20th? 1/20th, okay. So the answer is going to be 1 plus 2/5 plus 1/4 plus 2/20. Yes? This is not a way I would show a student to get them to understand. This is a lot wrapped up in it. This is a way just to kind of show a visual of mixed number multiplication instead of making it into improper fractions. This is actually a way to visually FOIL. So how do I do this? What's the LCD? Very obviously. 20. So this would be 1 plus what 20s? 8 20s plus what 20s? No. Yes. 5. Plus 2 20s, yes? So this would be 1 plus 15 20ths. So it's 1 and 3/4. Can somebody check? How do you check that answer? Well, can somebody give me the better way to do this? What's the better way to do this? to do this like computationally, what's the better way to do this? Turn each of these into, like you're about to do, Drew. Yeah, so it's be 5/4 times 7/5, yes, which is what? We know how to do this, yes. What would that be?
Yeah.
35/20 is what goes into both of those. 7/4. Yeah, okay. So it checks. Do you guys see what I mean though? This is a visual of the foiling that you would have to do if you kept them as mixed numbers. Okay. Maybe. So let's build on, now obviously I took what I knew you knew. I know you know how to multiply fractions, but we haven't talked about how to show students that. So here, watch this. What is, oh my God, John. Okay, let's try a clean sheet. Has everybody got this business? Yes? Let me try it. I'm gonna pretend like it was the paper's fault for why it wrote so horribly. What? There you go, see it was. What is 1/5 times 10? What is it? What's 1/5 times 10? All right, so if you do this visually, I would take 10, break it up into how many parts? Yeah. Break it up into how many parts? 5 parts. And if I count over, one of them would be 2. So what is 1/5 times 10? 2. And of course we know why, because 5 goes into 10 twice. Okay. What is, so extend that to 1/5 times 10 sevenths. So now you can say 5 goes into 10 twice. 5 goes into 10 twice. So what's the answer? 2 sevenths. Is everybody with me so far? So 1/5 times 10 is 2. 1/5 times 10 sevenths is 2 sevenths. I just threw in a sevenths. Yes? So it just makes it 2 sevenths instead of just 2. So I can extend that. So here, a side note. What is 7 times 1/7? The answer will shock you. What is 7 times 1/7? 1. So, finally, if I put all this together, 7/5 times 10 sevenths. So I know that 1/5 times 10 sevenths is 2 sevenths. I know that 7 times 1/7 is 1. So there's a lot going on here, yes? But we all should know the shortcut. If I do this, and then do this, and then do this, oh my God, that's a long ass way to go for the answer. Yes? You guys see every step I took? So I can multiply straight across. I could then use commutativity, and then I could break them back up. 7 sevenths is 1, and then 10 divided by 5 is 2. Now the shortcut is the 7s cancel. Why go all the way here to see they cancel? I could just cancel them. If it's on the top and on the bottom, and it's a common factor, they cancel. 5 goes into 10 twice. 7 divided by 7 is 1. And then, of course, 1 times 2 is 2. 1 times 1 is 1, and that's still 2. So that's our standard algorithm for multiplying two fractions, right? We reduce first. Do you guys remember that? Okay. Oh, no, we don't talk about all that. I sort of did already. Oh, now that we've done this, we can talk about what somebody else brought up earlier. Sorry, go ahead, Nick.
Sorry.
You're good. Distribution still works. So if I have like 1/4 times 100 plus 24, I could distribute if I wanted to. Yes? So 1/4 of 100 is 25. 1/4 of 24 is 4 goes into 24. So you get 30. Yeah, okay. You guys okay? You guys okay? All right. Okay, so let's get a little bit into division. I just want to do this real quick because somebody brought distribution up, but we can finally do it because now we know multiplication. Now, I don't have to tell you guys that I'm a major geek, but this shit excites the hell out of me, and of course it would. Dividing fractions, not an exciting topic, I know. But I love that this book does some stuff that I do. Let's start off with an easy one. Start off with an easy one. 8/13 divided by 4/13. Think about it in terms of missing factor. Yes? So the answer would be the number that I got to multiply 4/13 by and make it 8/13. Right? So how many 4/13 makes 8/13? How many 4/13 makes 8/13? 2. Done. So do you see how if they have the same denominator? So if I make this into a rule, if they have the same denominator, Jeff, not plus, dude. It just becomes that. That's what we just did, yes? You guys got it with me? If they start off with the same denominator, division's easy. Okay. It's when they don't have the same denominator, things get freaky. Okay, good. That's all the same stuff. Good. Ooh. Yeah. Okay. I could do an example like that. Oh, I could do an example like this. Perfect. So let's apply this idea. So what if I had 3/7 divided by 5/9? Do they have the same denominator? No. Can we make them have the same denominator? Can we make them have the same? Can we not? Are we not able? We have that power. Can I make 3/7 and 5/9? Can I build them up so they have the same denominator? Yes, totally. Are 7 and 9 relatively prime? Do 7 and 9 share anything? So what's the first two missing? What's 3/7 missing that 5/9 has? 9. What's 5/9 missing that 3/7 has? On the bottom, right? 7. So this becomes 27/63 divided by 35/60. Now let me answer something that I see in your eyes. Dear God, dear God, you don't do this problem this way. I know we currently are, because all we know is if they have the same denominator, I know how to divide it, correct? That is all we have officially talked about in terms of division, yes? You want to start your students off somewhere, and they know how to make like denominators, because if they're talking about dividing fractions, they freaking add and subtracted them by now. So they know how to make LCD. Does anyone, well, let's see, let's go a little further. This leads into what we actually do. So what happens here, can I use this rule? Are the bottoms the same? Yes, so what's the answer then? What's 63 divided by 63? 1. What's 27 divided by 35? I don't know. That's what this says. If the bottoms are the same, the answer is the division of the tops. Yes? Now let me ask you, this will be the last time we need to do today, I think. So where I push my luck with you guys. If I start over from the beginning, 3 7s divided by 5 9s, how would you actually do this? I'm pretty sure I showed you why you do what you do. In fact, there's a 3-word phrase you can use to remember how to divide fractions. Keep, change, flip. So how would you actually do this? Keep, change, flip. So what would it become? 3 7s times 9 5ths. Now, where did 3 times 9? Can you see 3 times 9 in any of the work that we did?
Yep.
Right there. Can you see 5 times 7 in any of the work that we did? Yeah. So there are connections to why this shortcut works when you compare it to the admittedly long ass cut. Yes? We know better than to make like denominators, but I can build off of that. You can start with, if they have like denominators, it's easy. So if they don't, make them have like denominators. And then you make the students do a few of these, and you go, can we see any patterns emerging? Can we try to improve on what we're doing? Don't you hope we can? And they'll all go, yeah, dear God. They might not say dear God. That would be weird. If like a 10-year-old says, dear God, teacher. Okay. All right, I think that's enough. You guys probably can't deal with more of me. Yeah, so next time we'll keep going. We made it a little bit into 6-3. I'm thinking the next, I'm wrong, aren't I? I can't remember when our next test is off the top of my head, but I think it's supposed to go to the end of chapter 7. I'm almost certain we're not going to make it. I don't remember. That's why I give those homework sheets out. Almost definitely not going to finish chapter 7 for the test, just to let you know how to prepare, how much homework we have. Alright guys, I'll see you all Thursday. Thank you for coming. We'll see how many people come on Thursday. Ella, are you out there? Oh yeah, Enoch is not coming back. And Abia, I haven't seen her.
Wait, did you say my name?
I did?
I think so.
What's
I
your name?
thought Ella.
Oh, Ella.
I thought you.
I'm
I
sorry.
don't know if I was just. No, you're fine. Thank you.
I did say your name. Oh, that's where you're coming up here. Okay, I'm sorry.
No, you're